So, yeah, so everyone. So, I want to ask, did anyone give me your email or not? So, is there anyone who did not write emails? No? Ah, yes. Okay, so last time, so let me check that it has been recorded. Yeah, so last time we studied the classical theory, and the main result of this study was the following. So if some action has if the action has some symmetry plus epsilon epsilon, thank you, g times phi s of phi plus O epsilon squared. Maybe better to write it this way, that it is parameter of the transformation. This is a infinitesimal transformation itself. Then transformation. So then there are more or less two situations. One is where this original transformation is so if epsilon is just a constant, in R or in C. And then the only thing which we can say is that action of action computed for epsilon made coordinate dependent will equal to the integral of epsilon of d mu epsilon of x g mu of x d2x. But if our original transformation was some holomorphic transformation, for example, conformal transformation, which depended on z and z bar, then we know that this integral should vanish for holomorphic epsilon and anti-holomorphic epsilon bar. So the consequence of this is that this variation of the action plus g epsilon of x again phi is so it splits into two parts. One is proportional to d bar epsilon times g plus g of z plus d epsilon bar g of z g bar of z bar. So such formula contains much more information because it tells us, for example, on the equation of motion we get a homomorphic and anti-homomorphic current. And now let us, so maybe, are there any questions? So probably I don't want to focus on this classical case. No, not a standard case. Maybe just say a few words, but we will be interested in such transformations, and we want to consider them already in the quantum field theory. So let us suppose that we have some theory with the action that has this symmetry, and we want to consider some correlator, like we want to consider a correlator of O1 of x1, O n of xn, and this correlator will equal to 1 over partition function integral over d phi. We suppose that our theory is Lagrangian and there is some basic field which is the integration variable e to minus s of phi O1 of x1 O n of xn. Now, if we just perform a coordinate transformation with this action, it will not change the integral. So you can write that it is d phi plus g epsilon phi e to minus s of phi, and let us immediately use this formula which you already know, And no, I don't want to track precise coefficients in the matter definition of all these currents, but let us put some coefficient in front of this current, which we'll use later, which we'll adjust later. So this coefficient is something times integral d bar epsilon g of z plus d epsilon bar g bar of z. Maybe of z bar. And the integral is over d2x. And also, all these fields are also transformed times O1 plus g epsilon O1 and so on, On plus g epsilon On. So, and now let us expand this integral up to the first order in epsilon. So, so in the most cases, this measure is invariant under this transformation. But if it is not invariant, we should demand that this transformation also transforms the measure in such a nice way. So even if something goes from measure, we can put it as a quantum correction to this current. So if measure is not invariant, it's called anomaly, but we should assume that this anomaly is taken into account explicitly as some quantum correction to the current. So these contributions from measure and from the action will be combined. So its original correlator plus I can already write it as a correlator. So the first term is this correlator O1 On, and here this contribution from the action integral or d bar epsilon j of z plus d epsilon bar d bar of z bar and plus we can write plus anomaly. Which can be put actually into the definition of this current. Well, this is one term, and another term comes from the action of this operator on the field under the correlator. So each one is transformed. So it can be written schematically like sum from k equals to 1 to n g epsilon hat case acting on this correlator. ON. So since it equals to original correlator, all this together should equal to 0. And
the definition of covariance in the case of non-term is possible. I mean, either if I have a filter or say an analyst, I can always redefine the covariance in order to use word.
yes, and if you have normally, I don't know how it is called, coming from scale transformations, then you can also write explicit transformation of measure using Liouville action. So it is also trackable. But I don't know about other anomalies. Oh. So, are there other questions? So, so now what we see, since these two terms equal to 0, we have that for any epsilon bar, we have that integral over d to x number d bar epsilon times g of z plus d epsilon bar g bar of z these fields, it equals to some to n g epsilon of this correlator. Okay, equal to 1 to n gk's. So we see that this maybe here it is better to integrate everything by parts and to put this it can be written equivalently as can be written as integral over d to x d bar g epsilon d bar g plus minus plus d epsilon bar g bar times everything else. So since in the right hand side we have only epsilon at epsilon probably the derivative that x1 and so on at xn, it means that a function which stays in the left hand side depends only on these points. So we see that d bar g are under this correlator. So O1 and so on, On, and dg bar under the correlator. They equal to 0 when x is different from the points of insertion of our fields. And if you want to see what happens around the insertion, so we are free to substitute any epsilons, and because this formula works not for homomorphic and anti-homomorphic epsilons, it's the general transformation with arbitrary coordinate dependence. So we have chosen it in such a way to be able to look at any point separately. So if it is some actual conformal transformation, then the right hand side should be 0. It should be symmetry. But the spot transformation gives something non-zero, and what it gives is written precisely here. So. Now let us do the following thing. Let us substitute first let us draw a picture. So we have point x1, x2, and so on, xn, and let us take one particular point. Let us take some point xk, and choose such epsilon that it is homomorphic around this point xk and is 0 everywhere outside of this point. So epsilon of let us call this decay. So it's homomorphic in decay, and equals to 0 outside. So what do we get after this? So here we have this integral, and integral over so let me think. So let us look at this expression. The bar of epsilon computed inside or outside of this domain decay is 0 because function is 0 outside and homomorphic inside. So the only contribution comes from the boundary of this domain, and this the bar on the boundary gives a delta function which turns this surface integral into a contour integral around xk. So the result of this substitution tells us that integral over dz around dk epsilon of z g of z plus epsilon bar z bar z bar with some coefficient and so on and so on. Okay, this equals to this sum of generators acting on a no, sorry. This equals to a single generator acting on the field K, the epsilon K O1 OK. So is it fine? And so, if we see such an equality for all K's, it means that we have an operator equality Actually, maybe it is better to write this transformation of a field as a combination of holomorphic and anti-holomorphic transformation. So probably I'll do this. So this is G hat K epsilon bar O1 and so on ON. So we have an operator equality. That integral around zk or xk dz epsilon of z j of z o k of xk. And here it's time to choose this normalization coefficient, and I will put it 1 over 2 pi I. So this integral equals to the action of this holomorphic transformation on a field OK. And this is called conformal Ward identities. So is it fine?
So when you integrate the part, like to the derivative of the A, okay, in principle, this should have it also O1 when I have one of them, right?
Oh, but it is some function which contains some singularities, but we can explicitly differentiate the singularities and say that we have delta functions. So this is precisely what is written here. That this is non-zero when this coordinate is different from x's, and it contains some delta functions. It can contain delta functions when so this x. Mm-hmm.
Is independent from the choice of the right?
Mm-hmm.
Already the definition of the correlation function that when fields have the same position also the function.
No, it's not necessarily delta function. They can have no when position of this current and some other field coincides. It's some pole, not a delta function. And delta function is or derivative of delta function is d bar of this pole.
Like when you have correlation functions, like in real case you have time ordering, right?
Mm-hmm.
And in this case that you have probably a radial ordering.
Yes, first.
Okay, so that's the source of the deltas when I integrate the part.
What is there some question or no?
Where we can
Because
no, it's fine.
but I think that if we are not afraid of differentiating delta functions, we can do this integration by parts always. Just to remember that as a result we can go get delta functions somewhere. Okay, so so we have this relation for homomorphic and anti-homomorphic Z. And so it says that transformations of fields are done by this conserved currents in the theory. And let us maybe consider some examples. So, or maybe we need to consider this free boson to be able to compute something in that example. So the action is given by with some coefficient which I don't want to specify. I will prefer to specify the correlator of two fields d to x, d phi, d bar phi, which is the same as d mu phi, of course, up to some coefficient. And if we want to compute a correlator of phi of x and phi of y, it will equal to the gain function of this, like again with some coefficient, the gain function of Laplace operator. And who knows what is the gain function of Laplace operator in 2 dimensions? Yes. So yeah. So if we choose normalization appropriately, it will equal to a log of now there is a good question which precise logarithm, because these variables have in principle some dimension, and if you try to compute inverse Fourier transform, it will also be a little bit divergent. So we should write something like this. So does anyone have a question about this, or everyone knows? So it is just a solution of dd bar log of squared x minus y squared equals to with some coefficient, again probably pi. I forgot delta 2 of x minus y. So we can switch to ideal coordinates or do a Fourier transform and compute this. So, but the answer is this, and it can be written as minus log of z minus w minus log of z bar minus w bar. Oh, sorry, x minus y, x bar minus y bar plus log of r squared. So it's kind of almost splits into a homomorphic and anti-homomorphic part. And on this R, which stays here, is some kind of infrared regularization of this theory, because naively, if you look at the section and the path integral for it, it has zero mode. If we choose phi equal to a constant function, it will not enter the action, and in principle we have this integral over zero mode from minus infinity to plus infinity. So the integral is naively divergent, so we should restrict it somehow. For example, pose some boundary conditions at infinity, or do something like this, which enters as this R into the green function, so that when x is approximately of order R, this green function tends to 0. So we can think that it is some boundary condition phi equals to 0 at very, very big distance. And if you consider the theory with some actual boundary conditions, then it will cancel. So it will not depend on any regularization. But now, so I want to do namely this field phi is of dimension 0, because classically we don't need to transform it, but because of this logarithm, it's not a very nice field, and we will talk about this later. But if you want some field which transforms under conformal transformations in a nice way, we can take, for example, a derivative of phi. So, namely, we take an expression dz d let us say that there is some current j of z which equals to I forgot, probably I d phi. And if we consider it as one form, g of z times dz, this one form will be invariant under conformal transformations. In a sense, it's written in the same way in all coordinates. And in principle, so it's example of a field with dimension 1, 0. And let us try to check what is the transformation law for this J of z if we try to perform conformal transformation. Namely, let us consider J of z plus epsilon of z times d z plus epsilon of z. It will equal to g of z dz plus plus epsilon dg dz plus d epsilon g and dz. So in this case, transformation property is g goes to g plus epsilon d, g plus d epsilon g. And if we have some field of dimension delta, which can be thought as such a form of weight delta. So what we will get for the transformation of this field? So O delta will go to O delta plus, well, who knows what this infinitesimal transformation will be. No, epsilon dj, no. Maybe vice versa, because when this is raised to power delta, it contributes to the term with derivative of epsilon, because epsilon is differentiated in this part. So this term, which is responsible for shifting of the argument, is epsilon d O delta. And then this other term, which is responsible for conformal dimension, is here. It is epsilon d epsilon O delta. So is it fine? So it is a transformation property of a field which behaves as a form of weight delta, and such fields are called primary. And now, if we want now let us first see what it means practically for this general formula. So here we see such a kind of formula, and in this particular case, when we study conformal transformations, this field J is energy momentum tensor. Remember that there is a T and T bar component of this energy momentum tensor. So homomorphic part corresponds to homomorphic component, and we have an equality of this kind: epsilon of z, t of z, O delta of x, equals to so we write this this change of field. It equals to epsilon of x do delta of x plus d epsilon of x delta d epsilon of x o delta of x. And if you look at the right and the left hand side and the right hand side, we can easily come to the concept of operator product expansion. Because you see, here we have some homomorphic function, and if we integrate, if we multiply it by the square root and integrate around point x, we see that for some reason in the right hand side we get this function at x and also its derivative at x. So this formula tells us about the analytic behavior of this product. Namely, if we say that tz times o delta of x equals to sum from n equals to minus infinity to plus infinity, some ln o delta some new operators of x divided by z minus x power n plus 2. It's a definition. Then this integral on the left hand side will equal to what? It will equal to the integral over x 1 over 2 pi i is that epsilon of z sum over 1 over z minus x to n plus 2 ln o delta x So, and what does this integral equal to? So, what will we get? Like, what will we get from this? So, the only terms which depend on z are this pole and this epsilon of z. What will we get as a result? So, it will be some ln o delta of x times times what? Well, of all derivatives actually. So yeah, so it will be epsilon. So what is actually? It will be n plus first derivative probably divided by n plus 1 factorial like this, I think. Of x. So and now, now we have this formula. So if you suppose that the expansion contains all these negative poles, then we get this in the right hand side. And if we now compare it with what it actually equals to for the primary field, we come to the conclusion that actually, here we should sum from yes, from equals -1 to yes. So yes. We see zero derivative for n equals -1. And this zero derivative corresponds to dO delta. So then we can conclude that L minus 1 acting on O delta equals to dO delta. Then L0. It is first derivative, and here is coefficient epsilon, coefficient delta, so it equals to delta, O delta, and all other else k greater or equal, or k greater than greater or equal than 1, O delta, they just include this field. So we see that on the following correspondence that a singular part of the OP it defines the action of the integral of motion on local fields and vice versa. So and now let us try to look at this example. So, in principle, we know that this field should be one form, but let us compare it with the prediction of CFT, like of the general theory. So another momentum tensor, which we already computed, equals to T of z, maybe. So we can write it either as either -1/2 d phi of z squared. We should take a normal order of it, so it makes sense. Or it can be written equivalently that it is 1/2 of g of z squared, normally ordered. By normal ordering, I mean, actually it's a good question what the normal ordering of fields is, because there is a normal ordering coming from bosonic or fermionic representation, but also this operator expansion gives its own normal ordering, and it is defined naturally that we should take a first non-singular term, which is we should take constant term of this expansion and denote it as a normal product of two fields, which works in any CFT. But now we don't need this. We can just say that it is a limit to when some I mean, delta goes to 0, 1/2 j of x minus delta over 2 j of x plus delta over 2 minus correlator. Like this. So now let us compute OP of this energy momentum tensor with the current G of W. So how it is done in the free boson theory. Oh, by the way, does everyone know Wick's theorem? So then, if you want to compute the operator expansion, we imagine that there are some other operators, like some arbitrary number of operators, some local fields staying under the correlator. And when we start to compute on this, get what? We get 1/2 g of z, g of z normally ordered, g of w times everything else. And it equals to what? So one option is to say that this 2j's pair with some other operators. This j also pairs with something else. So the first term is something like this: j of z, j of z, j of w, and all this. And this term is, of course, regular, because it does not contain a pairing between z and w, which can give a pole. And all other terms, when it pairs with some fields in other points, are regular. So then there are two equivalent terms when one of these j's pairs with this j. And since there are two, and this 1/2 is cancelled. So we have another term where j of z j of z pairs with j of w. And this last j pairs with everything else. And that's all. So we can conclude that it means that this OP T of Z with J of W equals to normal ordering J of Z squared J of W plus 1 over Z minus W. By the way, we need to compute the correlator of J of Z with itself. Oh, who can tell what it is? Just this? Yes. Yes. Because we take this logarithm and we first differentiate it in the first variable, we get minus 1 over x minus y, and then we need to differentiate in second variable, we get minus 1 over z minus w squared, and we also have these two i's, so in the definition of the field. So finally we get 1 over z minus w squared. Yeah, so here we have z minus w squared, and the field in the numerator is j of j of z. But this is not what we want precisely, because in this formula, this j of z stays at the first point, not the second one. Such expansion can also be invariant. It can also be useful. Not only for this field, but also for other fields of dimension 1. So it says that if we start to integrate instead not not t around j, but j around t, it so let me remember. Yeah, if you want to indicate j around t, we see that this denominator does not have a first order term, and so this integral in other variable will vanish. And for example, it is used for construction of scanning charges. But now we need to rewrite rewrite this OP in the standard way. So this term is regular, so we will not write this. So T of z, J of w equals to J of w over z minus w squared plus first derivative dj J of w over z minus w plus something regular. So you see here there are no surprises, right? And but now let us do another computation. So we've already seen a field of dimension 1, 0. So J of z had dimension 1, 0. But let us ask the same question about the energy momentum tensor. So namely, it's a product of two fields, J and J, and we expect that it's of dimension 2, 0. But probably most of you know that it is not true. It is not a primary field, and if you try to compute its OP with itself, we will see some surprise. So this OP is what? It's 1/4 J of z, J of z, J of w, J of w. And now let's start from the most singular terms. So the first term comes from pairings between this j's and this j's. And there are two ways to do this pairing. One way is this one. Another is maybe no. Let me write all these terms. So one way is in this. Like this. So there are two such terms. Then it have four terms with a pairing of one of these fields with one of this. Plus 4 times 1/4 J of z, J of w. Oh, sorry, J of z, J of z, J of w, J of w. So these two are paired. Plus something regular. So the first term equals to 1/2 over z minus w fourth, and that term equals to j of z, j of w normally ordered, because we cannot pair them anymore. All pairings are in the first term, over z minus w squared. So plus regular, and so now we need to expand around the second point, and it gives us J of W squared over Z minus W squared plus dj of W, J of W or Z minus W plus regular. So who is this term? What does it equal to? Yeah, thanks. So it is T of W over Z minus W squared. And this that's dt of W over Z minus W. So we see from here that even if a field looks classically primary, if it seems that it has dimension 2, it can happen so that at the quantum level it has some non-trivial transformation property, some non-trivial transformation law. And if we go back to this conformal word identity, we can find the infinitesimal form of this transformation law. So, namely, we can see that so I forgot to say that this is the general OP of an argumental tensor, and in the general case there is some central charge, so some number stays here. So in our case C equals to 1, this boson. So if you try to recover transformation properties of T, then we see that it transforms like a normal primary field. So So there are this general transformation with arbitrary dependence of epsilon, but there are also transformations that are automorphisms of complex sphere, where our theory lives. And if we do such transformation, like if we, maybe I'll erase all this. So let us choose this epsilon of z to be infinitesimal form of a global transformation. So in this case, our correlator, so what we get? On one side, we get integral d phi O1 and so on On e to minus s of phi. And if we perform the change of variables, then we get 1 over z phi e to minus s of phi plus g epsilon phi, sum of g k's epsilon acting on n. But since this is the actual global transformation, then the section does not change. Of course, together with measure, but we say that again these two are preserved. And the only term which remains is sum of these j epsilons acting on all fields. And plus the initial correlator. So it equals to O plus sum of the epsilons acting on this correlator, which means that so we compare it with what it was, and it was this correlator. So now that sum of this g epsilons k on O1 and so on OK On equals to 0 when epsilon is global. So in this case of the theorem sphere, I've told the last time that global transformations are fractional linear maps because it should give one preimage for 0 and one preimage for infinity. So it has one pole and one 0. So let me check. Oh, it's recorded. So a three-dimensional group, like maybe PSO2 or PGO2 of C. And if you want to write some simple some infinitesimal transformations, we should perturb this identity matrix when ABCD equals to 1, 1, 0, 0. And these perturbations are the following. F of z is 1 plus epsilon times z. F of z equals to z plus epsilon, and f of z equals to one parametric groups equals to 1 over z 1 minus epsilon z. So as a consequence, the corresponding vector fields are maybe it's better to swap these two. Maybe so. Corresponding vector fields are 1 z squared. So now what are possible ways to think about this? One way is to say that correlators in arbitrary CFT satisfy three global world identities, so they should depend on n minus 3 variables. Another way to think is that we can use this group to bring all fields to positions 0, 1, and infinity, or maybe start with to some point big R, and then send it to infinity. And after this, express all other all other values in all other positions of points through this one. So for the global SO2 transformations. I don't know, maybe it should be something very pathological. Well, if you do this with a non-conformal theory, then of course it will have anomaly. But like even starting from this transformation. But in CFT, I think no. So let us try to find the general form of two-point function in CFT using this argument about the global transformations. Probably I can raise this. So let us try to compute some correlator of two fields, O delta 1 of Z1 and O delta 2 of Z2. So if we multiply it by dz1 to delta 1, dz2 to delta 2, it should be invariant. Let us call it some omega, no, some omega, and this should be invariant on the this conformal transformations. Thank you. So first of all, we see that it is a translation invariant because we have such transformation. So this it gives us that omega should equal to some function of z1 minus z2, z1 to delta 1, z2 to delta 2. And then it should be invariant under scaling. So f of lambda z1 minus lambda z2 dz1 to lambda delta sorry, lambda to delta 1 plus delta 2 dz1 dz2 should equal to f of z1 minus z2 dz1, delta 1, delta 2, dz2 to delta 2. And from this we get that this function should be this omega should be dz1 to delta 1, dz2 to delta 2 over z1 minus z2 to delta 1 plus delta 2. So far we used only two transformations, but now remember that this fractional linear transformations also contain the inversion of z. There was a transformation z to z inverse. It was there. So now try to do this transformation z to z inverse. This omega maps to d1 over z1 to delta 1 d1 over z2 to delta 2 1 over z1 minus 1 over z2 to delta 1 plus delta 2. And so finally, if we pull the z1 and z2 from the denominator and combine with what comes from the numerator, we get z1 minus z2 delta 1 plus delta 2 dz1 to delta 1 dz2 to delta 2. So, and who can track powers of z1 and z2? What do we get as a result? So I'm saying that we get not only this term, which is what we had initially, but we will get some correction. So who can track this correction? Hmm? Hmm? No, which sign? Oh, we have so we have 1 over z squared here. Hmm? Yes. So it gives us z1 over z2 to delta 1 minus delta 2, right? Minus delta 1 plus delta 2, right? The consequence of this is the following: this is that it does not equal to initial correlator unless delta 1 equals to delta 2. Delta 1 should equal to delta 2. So the consequence is that O delta of delta 1 of z1 O delta 2 of z2 is equal to delta 1 delta 2 over z1 1 minus z2 to 2 to delta 1. And actually, I did not pay attention to the anti-homomorphic part of this calculator, but we should also multiply it by anti-homomorphic part with z bar and probably with some other dimensions, delta bar. Like if they were fields like J of Z, they would have dimension 1, 0. So it will be just z1 minus z2 squared. And if you look at this form omega that we get in this case when these deltas coincide, then it equals to dz1 dz2 over z1 minus z2 squared, everything to power delta. And this expression written here is called the Bergman differential. So in our case, it lives on a sphere, and there exists only one such form, which has a second order pole diagonal with coefficient 1 and homomorphic outside. And only homogeneous surfaces there exists some family of these forms because we can add homomorphic forms. But one canonically normalized Bergman by differential always exists. And for example, here we can get it by computing a correlator of two currents in the theory of free boson. And in the general case, we can do the same, like put a free boson on a Riemann surface and compute the correlator of two currents. So, are there any questions?
On the invariance and the rotation means that we take the modulus of the one.
Yes. So
in the final form of omega, the dependent is like the
no, we consider homomorphic and anti-homomorphic parts separately. So, for example, here, when I write this transformation, f of z goes to 1 plus delta z, it can be either dilatation or rotation. So we can transform z to lambda z, and lambda is real, or we can consider z to e to I phi z. So everything is combined. And you see that if you add here anti-homomorphic dimensions like delta bar, z bar, the eigenvalue for this dilatation will be sum of dimensions, and the eigenvalue of the rotation will be the difference of dimensions, which is called spin. So Uh, so this two-point function can be computed this way, and you also see that since we can choose fields in arbitrary way, there is some quadratic form on the space of fields, and we can adjust them such that this quadratic form is diagonal. So we can always normalize fields such that their two-point function is diagonal. And also one last point that you see, we could find the two-point function based on the general assumption of invariance, and we can also do the same for the three-point function, because all 3 points can be sent to 0, 1, and infinity, or some other point, and so this function should be proportional to something universal times times some constant which depends on fields. And let us try to construct this universal object. So we already have this Bergman differential, which is well defined on a sphere and is holomorphic and has a correct well, how to say it? So it is conformally invariant, and it's homomorphic outside the diagonal. So we can combine the correlator of 3 fields from such Bergman differentials. So namely, let us try to write this. Times dz1 to delta 1, dz3 to dz2 to delta 2, dz3 to delta 3. And now the product of the answer. So dz1, dz2, or z1 minus z2 squared, dz2, dz3, z2 minus z3 squared. So now we only need to adjust these powers. And if I remember correctly, it is, so let us check this later. It is delta 1 plus delta 2 minus delta 3 over 2, delta 2 plus delta 3 minus delta 1 over 2, and delta 1 plus delta 3 minus delta 2 over 2. So let us check. So for example, z1, sum of this power and this power is delta 1. So it is correct. So and it is multiplied by some constant, which cannot be removed by any scalings of fields, because we used all this freedom to diagonalize the point functions. So 3-point functions are dynamical parameters of conformal field theory. So maybe that's all for today. Do you have any questions?
Sorry,
Hmm?
this is like I think I missed the part about the diagonal differential. Like, does it exist on any nuance?
Yes. And we can write a formula for this. Let me think. Actually, so if you want to here p of z w is d z dw of logarithm of a theta function with odd characteristics, so that it vanishes at 0, of log of theta star of abelian map of z minus abelian map of w. It's not the full truth, if I remember correctly. But I forgot what should precisely be written here, and probably I'm missing the differentials, but probably there should be some combination of homomorphic differentials also. Yes, product of them. So a typical expression which can appear here is mm, mm, but so there is a expression like omega times d d over this vector, which is in the argument of theta star, and this is the vector of homomorphic differentials. Of 0. But let me actually check this because I forgot what are the periods of this logarithmic derivative. So Bergman differential is normalized by requirement that its a periods are 0. Based on this, we should add something to this logarithmic derivative, if I remember correctly. But I need to remember what precisely. Mm-hmm. Welcome. So, any other questions? Okay, so thanks for the attention. And probably did any of you see the announcement? We will be in different rooms in next times. Sometimes it will be 134, sometimes it will be 136. And I forgot which day, which room. Okay.